Alrighty, so for this week, we have two sections to get through. So this will be this section point five is the last one that will technically be on the first exam. So this stuff can be included, but the point of section 7.5 is that this is just really a bunch of it's supposed to be helpful advice to give you kind of a way to evaluate these integrals. In the sense that, if I hand you a problem and ask you to integrate, you're not going to know what strategy to use because I'm not going to tell you what section it comes from. And so what this section does is goes through some of the things you're supposed to look for when you're doing these integrals. So the first thing you should notice, when you're looking at this section, there's this big table of integrals. And the idea is you want to have most of those memorized or, know how to derive most of them. Um, you are allowed to use your book for the exams and quizzes. So, right now you can, use this table, but, none of the problems I'm going to ask are going to be, integrate this function. Um, so you're going to have to, be a little more clever than just looking at this table and being able to find the answer. Okay, so let's just jump into this section. This is a short one. It's called Strategies for Integration. It just goes through and gives, a couple steps to do, just a couple things to look for, um, and what to do when you notice those. So the first one is simplify the integrand. So what this means is, if you had something like the integral of the square root of x times 1 plus the square root of x. You might, if you see this, hopefully you're not going to try a u substitution. What you'll notice is that you can, distribute this and you get the square root of x plus x dx. And so this is the integral x to the 1/2 plus x dx. And both of those are, integrable. You can just do the integration. So that's really the first thing you're looking out for. You want to make sure that these things can be, or cannot be simplified into something that's really easy to integrate. So another example, this is trig integral. You have tan theta divided by secant squared theta d theta. And so, you look at this and you say, okay, you might start running through your list in your head already, say, well, u substitution might look like it works because I have, the derivative tangent secant squared, but the problem is, secant squared is in the denominator. I would need it in the numerator for a u substitution to work. So what you can do with this one is, so I always, write things in terms of sines and cosines first. So this is sine theta over cosine theta from the tangent, and then 1 over secant squared is cosine squared theta d theta. And then this is the integral when you simplify sine theta cosine theta d theta. And you can use u substitution on this if you want, but there's a trig identity that says sine theta times cosine theta is going to be 1/2 sine of 2 theta. And now that's integrable. And there are some more examples, but again, they're just things that you are um, trying to simplify here, so you don't have to do anything more advanced. So again, one is just simplify, see if it turns into something that you can just integrate directly. And again, on our exams, I'm not testing you on being able to simplify these things. I'm testing you on, integration by parts, trigonometric substitutions, things like that. So hopefully, as long as I'm writing these problems correctly, you won't be able to just do a simplification. So number 2 is, the first step I always go through. Look for u substitution. So again, so just as an example, so look for u substitution. Does f, and so this f of x and f prime of x appear in the integral. So as an example, we have the integral x over x squared minus 1 dx. You can notice here that you have, x squared minus 1 here, and if you think about, what's the derivative of x squared minus 1, that's going to be 2x, and, you have that x appear up top. That tells you that this is going to be a u substitution. So this one would be u, it's equal to x squared minus 1, du is equal to 2x dx. And then you would just use the strategy that we know what to do. So, again, be careful. One of the things you might do, because, what we've been talking about, is you would look at this and say, okay, that's a rational function. I can use, by parts, or I can integrate, or not, sorry, not by parts. I can use partial fractions and split it up to get, two things that are easy to integrate. But that's not necessary in this case. You could do it. I think it probably works. Yeah, it works. But it's going to be, a nightmare. Okay, so let's just continue on. We'll get through most of these. This is a short chapter. The next chapter is, so not the next chapter, but 7.9, 7.8 is the next one we're doing. It's a lot more interesting, and it's actually new stuff. So 3 is classify the integral if u substitution doesn't work. So, do I have trig functions? This isn't trig substitution. This is, do I have trig functions? Can I use any of the rules I learned from section 7.2? So, do I have an even power of cosine, odd power of sine? What do I do in those situations? Really, all that comes down to is rewriting your functions there and looking for a u substitution. So rewrite functions. Look for u substitution. So that was, just things of those forms were, trig functions. B is, do I have rational functions? That's of the form p of x divided by q of x, where, p and q are polynomials. If I have rational functions and I can't use a u substitution, like I talked about up here, if I can't use a u substitution, like I could in the example in the middle of the screen right now, then I could use partial fractions. And then I can integrate those because they come out in, things that usually turn to logs or things that I can use u substitution on. So this one is partial fractions. So let me start writing the form and then the strategy in a different color. C is it an integration by parts? And for this one, what you're looking for. So there are a couple different forms. I'm going to write them in black. So you could have something like, x cubed e to the x. And the point of this one is if I differentiate x cubed enough times, then it'll go away, it'll disappear. If I differentiate it 4 times, then it becomes 0. And I can integrate e to the x, however many times I want. It's not hard. And so this is a good problem for integration by parts because I can make x cubed disappear by differentiating it 4 times. And that's what integration by parts is. It lets you differentiate one thing, integrate another thing, and you can do it as many times as you want. So that's one of the things that you're looking for. You could have, something of the form e to the x cosine of x. And this was something we had to use integration by parts on. We could, the reason this worked is if we, integrate, let's say differentiate, because it's easier thinking in terms of differentiation. If you differentiate cosine twice, you get cosine again with a minus sign. And so that's helpful in the fact that this sets up an equation to solve for our integral. And so, there are a couple examples, and that one is section 7.3. So when you're studying, you can go back and look at these. No, sorry, section 7.1. I did an example just like this, so you can go back and check it out. But the idea is I'm able to set up an equation with the integral on one side, the integral on the right, or the integral on the left hand side, the integral on the right hand side, and then I can use that equation to solve for the integral. And so that's what we're looking for. Can I differentiate one thing, integrate the other thing, and end up at some point with the same thing again? So I can differentiate cosine twice and get negative cosine. If I keep integrating e to the x, I'm going to keep getting e to the x, and that allows me to get an equation to solve for. Lets me get an equation to solve for e to the x, cosine x. And then the last one that I'll kind of point out, I think there was an example like this on your, so this is all still by parts. So it was on your homework, it was something like this, ln of x squared over, let's say, x to the fourth. This is by parts also, and the reason I know that is because 1 over x to the fourth I can integrate. I know how to integrate that. And if I differentiate ln of x twice, if I differentiate ln of x squared twice, I get something in terms of 1 over x or 1 over x squared, terms that look like that. And so that'll end up, when I do the integration by parts, that'll end up giving me something that I'm going to have terms of like 1 over x to the fourth, 1 over x to the fifth, 1 over x to the sixth, and all of those I can integrate directly. So yeah, so those are kind of the things I'm looking for with integration by parts. And again, this last one was something I got from your homework. It's a good example to know how to do. So there are just a couple more for this. Or no, sorry, we're at part D now. So D is radicals. Do I have radicals that appear? So A is if it's of the form square root of plus or minus x squared plus or minus a squared. It doesn't just have to be a square root. You could have to to the fifth, 5/2 power, things like that. Then this is a trig substitution. So trig substitution, I'm looking for radicals. Typically, they don't have to be radicals. If the radicals aren't there, they end up usually being just the arctan or the arc cosine when I integrate them. But so if I have something of this form, square plus or minus square root of, plus or minus x squared plus or minus a squared square root, then I'm looking at a trig substitution. The square root is really what jumps out at me, and the square root plus the x squared. Okay, so sorry, that shouldn't be an a, that should be a 1. We've already done a. And then 2, if it's of the form, so we have the nth root of ax plus b. Then you use substitution. U is equal to the nth root of ax plus b. And sorry, this is not n times the radical. This is the nth root. Just make that clear. So it's like cube root, fourth root, fifth root, whatever. You're gonna try. You're gonna try this. It might not work. It might. This is kind of the point of integration. And so step four, you've done all those. Step four is to try again. And we're gonna, as I've done all these problems, I've told you what I'm looking for, why I know, I don't just say, this is section 7 point whatever, this is the method we're practicing, this is what we're gonna use. I always kind of try and tell you what I'm looking for that tells me that it's the, whether it's a trig sub or a integration by parts problem. I tell you what I'm looking for. And so, after you've done all this the next step is to try again. And that's the unfortunate thing for integrals. So differentiation, even if you weren't great at it, in Calc 1, it was something that was, it was straightforward. I looked at something, I applied the rules I knew, and I either could or couldn't get the answer. And I knew I would know whether I could or couldn't get the answer, depending on whether or not I knew, what a derivative was. You know, being able, so like knowing like what the derivative of a function is like what limits me with differentiation. Integration is much harder. So integration, we're trying to undo differentiation. And there is no straightforward, do this, this is the rule, it's try this, did that work? Okay, no, try this, and you just keep going until something works. So with these problems, you really want to, do a bunch of these problems to get used to, what you're looking for, because then you can't be tripped up. So I'm going to stop the video here, then there are some examples. I'm trying a new method of recording, I'm just recording my screen. I'm terrified right now that I'm talking and it's not recording audio. So I've just wasted 15 minutes or however long I've been talking for. So if I like this, I'm going to stick with it. If not, I'll go back to Zoom. But I'm going to stop the video here.